Hello, welcome to PhysQuest. So in this video, we will discuss about the step-by-step process to solve any contour integral involving residue theorem. So first of all, what is the definition of the residue theorem, also known as the Cauchy's residue theorem? So as per Cauchy's residue theorem, it states that if a function fz is analytic inside a simple closed contour C except for a finite number of singularities, see, this is a contour C. A function fz is analytic inside this contour except points noted on the contour. At these points, the function fails to be analytic. That is, they are the singularities of the function. So when such a function is integrated over a closed contour, then integration over the function over the closed contour, that is integration over C fz dz, is equal to 2 pi I times the sum of the residues of the function at all the singularities within the contour. So this is the definition. Now here we will discuss how to solve such type of problem in step by step. See, here identifying the singularity is not important. Important is the type of singularity we need to find out the residue and how to identify that particular singularity. So please watch this video till the end. Okay, so now here we understand this through an example. So let's do that. So we have taken the example of an integral z square sine square 4z dz for contour, that is a circle centered at z equal to 1 by 4 and radius is pi by 4. So first of all, step 1 is find out the singular points. So the function here is fz is equal to z square divided by sine square 4z. Now to find out the singular points, we have to set the denominator as 0. So sine square 4z is equal to 0. This is possible when this is equal to sine square n pi, which shows that 4z is equal to n pi. That means z is equal to n pi by 4 for n is equal to 0, plus minus 1, plus minus 2, plus minus 3 and so on. So this, if you write it down properly, so this shows the singular points are z is equal to 0, pi by 4, pi by 2, 3 pi by 4, etc. Now we have got all the singular points of the function. Now next step is define the contour and check out of all the singular points which of the singular points are within the contour, because that is what are important. The singular points outside the contour are not required, because residue at those points will be definitely 0. So we only need those singular points which are within the contour. So we have got a set of points 0, pi by 4, pi by 2 and so on. So out of them, which of them are within the contour? So in this case, if you draw the axis, we have our circle centered at z equal to 1 by 4 and radius pi by 4. So this is z equal to 0 and center of our circle is z equal to 1 by 4. So this point is z equal to 1 by 4. So when we, and radius is pi by 4. So when we draw a circle, this is the radius pi by 4. So this is our contour. So if you observe here, z equal to 0 is within the circle. Also z equal to pi by 4 also will be within the circle, because from z equal to 0, this distance is pi by 4 and this is 0. So from 0 to pi by 4, if it will be somewhere here, so definitely it is within the contour. Rest of the points are outside the contour, so we don't need them. So we have got our required singular points, that is z equal to 0 and pi by 4 are within the contour. Now comes the important step, that is check the type of singularity and find out which of them are poles. So because only poles contribute to form a residue of the function. So other type of singularity will not give the residue value. So that is why it is important to find out, to differentiate, you should understand that how to differentiate between different type of singularity. And I have chosen this example because the singular points are different here, because one kind of one is a pole and the other is another type of singularity. So we need to choose those singular points which are only poles. Now here, before choosing the pole, you must first of all understand what is the Lorent expansion. Suppose fz is an analytic function in a domain D except at a single point z0. So then there exists a region, that is its nearby neighborhood, which is defined as z minus z0 less than r but greater than 0, in which the function is analytic. So here we have an isolated singular point z0, as you can see in the picture. So define a circle around that is centered at z0 and its radius is r. So like this. So if you define a region within that circle in which the radius is greater than 0 but less than r, in this region the function is analytic. So in that scenario, such a type of function can be explained or defined in terms of the expansion like this. So fz is equal to summation over n equal to 0 an z minus z0 to the power n, summation over here, there is a mistake here, this is n equal to 1, summation over n equal to 1 to infinity bn divided by z minus z0 whole to the power n. So this is known as the Lorent expansion. Now this term, the second term, this term is known as the principal part of the Lorent expansion, and this is what is used to classify between different type of isolated singularity. Now here there are three type of isolated singularities. That is removable singularity, poles, and essential singularity. Now let us understand each of them. Removable singularity, as the name suggests, this is the type of singularity which can be removed. Then pole. Pole is something which makes the denominator of the function as 0. And essential singularity is something which is neither a pole nor a removable singularity. So now to understand it mathematically, we have to understand through the limit of the function. So now let's do that. So first of all, let's talk about removable singularity. So first of all, when you take the limit of the function fz for z tends to z0, this gives a finite value, which case in case of removable singularity. So whenever you got any singular points, so take the limit of that function at z tending to that particular singular point. If it gives a finite value, then this singularity is a removable singularity. Now another method is in terms of Lorent expansion. Now I have this as I said, this principal part is important here. If this principal part will be helpful in classifying different type of singularity. So for removable singularity, in terms of Lorent expansion, if you want to understand, then there are no terms with negative powers of z minus z0. Which means what? That means if we do the Lorent expansion here, the whole term, there will be no principal part here. So if any function, if you expand and it does not have any terms with negative power of z minus z0, this clearly shows that that singular point is a removable singularity type. So next consider about poles. So now pole is something, as I said, which makes the denominator 0, which means denominator is 0 means what? That function goes to infinity. So in terms of limit, we can say that limit of the function z tending to z0 is equal to infinity. In that case, the singular point will be considered as a pole. Now it can also be defined as, if you take the limit of the function z tends to z0, z minus z0 to the power m, f of z will be equal to a finite value. Now here, in that case, z0 will be considered as a pole of order m. And if m is equal to 1, then it is considered as a simple pole. Again, in terms of Laurent expansion. In terms of Laurent expansion, the principal part here, the Laurent expansion, if you consider for poles, this principal part will have finite number of terms. That means this part will have finite number of terms. Or you can say, in other words, there are finite number of terms with negative powers of z minus z0. Then last one is the essential singularity. Essential singularity, this is neither a pole nor a removable singularity. Now in terms of limit, if you do that, limit of the function does not exist. In case of removable singularity, when you take the limit z tends to z0, it is finite. In case of pole, when you take z tends to z0, the limit of the function goes to infinity. But in case of essential singularity, the limit of the function does not exist. Now in terms of Laurent expansion, here it has infinite number of terms in its principal part, or in other words, it has infinite number of terms with negative powers of z minus z0. So differentiate this carefully. In case of removable singularity, there are no terms with negative power of z minus z0. In case of pole, there are finite number of terms with negative power of z minus z0. In case of essential singularity, there are infinite number of terms with negative power of z minus z0. So this is how you have to differentiate between different type of singularity. Now the example we have chosen, we have got two singular points which are within the contour, that is z equal to 0 and z equal to pi by 4. So now we will check each of them, which of each of the singular points comes under which category. And remember, we only need poles. Okay, so let's do that. First let us check z equal to 0. So now we will check limit z tends to z0, the function. So limit z tends to 0, z square divided by sine square 4z, because that is the function, and we are considering the z0 here is 0. So limit z tends to 0, z square divided by sine square 4z. So when we do that, here from now you can write it down, the numerator will be the same z square, but sine square 4z we can write down the expanded form of sine z formula. So this will be equal to limit z tends to 0, z square divided by 4z minus 4z cube by 3 factorial up to so on, the whole square. Now if you look carefully here, from denominator, if you take common z, when it is taken out of the bracket, it will form as z square, and in the numerator we already have a z square term. So z square will get cancelled. So this can be written as limit z tends to 0, 1 divided by 4 minus 64z by 3 factorial up to so on, whole square. So which ultimately gives around, it's a finite value, whatever it is, it will be finite value. So as we have discussed earlier, that when limit z tends to z0, the function will give a finite value, it means it is a removable singularity. So this clearly shows that z equal to 0 is a removable singularity. Now removable singularity will not contribute towards the residue theorem. So that means this singular point we don't need to consider. Now next check for z equal to pi by 4. So here first we'll test for z tends to z0 function of z, what value it gives. So when we do that, limit z tends to pi by 4 z square divided by sine square 4z, this tends to infinity. So this kind of satisfy the criteria of a pole. Now, but to confirm that, what we will do is, see, in the denominator we have the power 2 sine square 4z. So what we will do is, we take limit z tends to pi by 4 z minus z0 to the power m f z we have discussed. So here z minus pi by 4 square into z square divided by sine square 4 into z minus pi by 4. So this term z square we have written like this, z minus pi by 4 plus pi by 4, and this definitely we have to write sine square 4 z minus pi by 4. So now what we can do is, here the numerator, consider this as, suppose this is a and this is b, so a plus b square formula will apply here. So, and in the denominator we will write down the expanded form of the sine z function. Okay, so if we do that, this expression will be like this. So this is limit z tends to pi by 4 z minus pi by 4 square z minus pi by 4 square to z minus 2 into z minus pi by 4 into pi by 4 plus pi square by 16. So a plus b square formula, a plus b whole square formula we have written here. Here a is z minus pi by 4 and b is pi by 4. And the denominator it will be 4 z minus pi by 4 minus 64 z minus pi by 4 cube divided by 3 factorial, and so on. The term is taken square of. So now in this case, what you can do is, in the denominator, here in the denominator, if you take common this z minus pi by 4 term, after coming out of the bracket it will be z minus pi by 4 square, and here we already have a z minus pi by 4 square term, so both of will get cancelled. So ultimately you will have expression like this, that is z minus pi by 4 square plus 2 z minus pi by 4 into pi by 4 plus pi square by 16 divided by 4 minus 64 z minus pi by 4 whole square divided by 3 factorial. The term is whole square. So this term, when you put the limit, will give a finite value now. So now we can say that this satisfies the criteria. See here, for this singular point, limit z tends to z0 f of z tends to infinity, and limit z tends to z0 z minus z0 square f z tends to give a finite value. So we can say that z equal to pi by 4 is a pole of order 2. So this is a this singular point will contribute towards the calculation of the residue of the function. Now comes the final state, that is calculation of the residue of the function. Now when we talk about residue of a function for a pole of order m, the formula is 1 by m minus 1 factorial limit z tends to z0 d m minus 1 by dz m minus 1 z minus z0 to the power m f of z. So here in case of this, here we have a pole of order 2, that means m is equal to 2. So this will be equal to 1 by 2 minus 1 factorial limit z tends to pi by 4 d 2 minus 1 by dz 2 minus 1 z minus pi by 4 square into z square divided by sine square 4z. So here I am not going through the whole calculation part. Ultimately when you do the final calculation, ultimately it will give you the value of pi by 32. So now as per the residue theorem, when you do as per the integral term, this will be the function, when you integrate it, it will be 2 pi I times the sum of the residue of all the poles within the contour. We have got a pole here that is of order 2 and calculated the residue. So ultimately this integration, the residue is pi by 32 we have got. So as per residue formula, the integral will have value 2 pi I times the residue, that is 2 pi I times pi by 32, which gives the value I pi square by 16. So in this video we have taken an example of a function which has different type of singular points, and we have carried out a step-by-step procedure for Cauchy's residue theorem and calculated the value of the integral. So in any examination, in any question which involves this kind of Cauchy's residual theorem formula, in that case please follow this kind of steps so that it will be helpful for you to carry out such type of problems in general. Okay, thank you.